So hello everyone. Sorry for that I were not able to make it in person. It's always better. My name is Shmuel Bialy. I know some of you. I'm from the Technion in Haifa in Israel. And I want to continue this thread talking about ionization and more specifically about cosmic rays. More generally, just before I dive into cosmic rays, I'm interested in anything, or any forms of feedback and how stars shape interstellar gas. So cosmic rays is part of that, but also UV radiation and turbulence, all these topics. That's the things we are doing in my group. And you heard, I think yesterday or 2 days ago, my student Jonathan Celeste talking about phases of the interstellar medium and the 3D map of temperature that we built. But today, as promised, I'll talk about cosmic rays and specifically about low energy cosmic rays. And why do we care about cosmic rays? So maybe most of you know already, but I'll discuss it quickly. So the cosmic rays and specifically lower energy, so about 10 mega electron volts to about a giga electron volts, are the most abundant cosmic rays in the galaxy, and they can penetrate deep into molecular cloud cores where UV radiation cannot penetrate, right? We have always the people talking about PDRs, PDR region, photodissociation regions, PDRs, UV, excitation, ionization, emission. But actually, if we talk about the regions that form stars, dense cloud cores, they absorb the UV at the envelope. And what can penetrate is these more energetic particles, cosmic rays. And what they do is they ionize the gas, producing very rich chemistry, forming all these molecules that we just heard in the last talk. They are very much affected by cosmic rays, and cosmic rays initiate all these chemical pathways by introducing ions and electrons into the gas. And then these ionizations by cosmic rays also heat the gas. It's the dominant and maybe the only heating mechanism of these dense regions. So the ionization basically just, eject electrons that then thermalize and heat the gas. So the thermal state and the chemical state are governed by cosmic rays. Also, the dynamics are governed by cosmic rays, because if not for the cosmic rays, the gas would be neutral and would not care about the large-scale magnetic fields of the galaxy. But once you have cosmic rays, they produce ionization, and then you have some charge, and the cloud already feels the magnetic field. So also the dynamics are affected and governed by the cosmic rays. Basically, this is all to say that the cosmic rays are very important. What do we know about these cosmic rays? Well, we have the local measurements, like the space station and Voyager spacecrafts that measure the spectrum of cosmic rays across decades in energy. So here at the left, I show the flux of cosmic rays are measured by Voyager and the AMS experiment on the International Space Station. As a function of energy, the energy range we really care about is G, V, and down, because that's where most of the particles are. And on the other hand, the energy is high enough for the particles to be able to propagate into molecular clouds. So this is the sweet spot. The problem is that at these low energies, it's also difficult for them to propagate and reach Earth. Well, that's part of why we need Voyager. So the Voyager observations constrain the spectrum at these energies. That's the black points you see here. Yet it's still quite uncertain what is the real shape of the spectrum for the general interstellar medium in the galaxy. First, because there is still some debate whether the Voyager spacecraft made it into interstellar space, or are they still affected by local solar modulations? And second, because even if they did make it to interstellar space, we are still located in one specific special point in the ISM. We are in the hot local bubble, and also it's just one point. So the question is, what is the characteristic spectrum and intensity of cosmic rays at the energies we care about? And here the blue, red, and green lines are some theoretical predictions of what could be the spectrum at these low energies, and we truly don't know. It's an open question in astrophysics. And different, they also, I indicate here the different slopes of different models. This is by Padovani, and also the associated energy density or energy density of cosmic rays for these models. So it ranges between about a half to over 2 eV per centimeter cube. So this is the question we want to answer, right? What's the intensity of the cosmic rays? Often parameterized through this parameter called zeta, the cosmic ray ionization rate per particle. So what do we know about zeta from the interstellar medium, right? First, we talked about the solar system. For the interstellar medium and the Milky Way galaxy, people did a lot of work, and some of it we heard also in this conference, on constraining the cosmic ray rate through different molecules. There are different methods spanning different kinds of molecules. So some people use H3 plus for more diffuse regions, use HCN, HCO plus, OH plus, H2O plus, argonium, different molecules. And the idea that all these molecules that I mentioned and more are sensitive to this parameter, to the zeta, to the ionization rate. And then you observe these molecules with spectroscopy from the ground or from space. You observe them, and then you obtain the column density of a molecule. You compare with the chemical model, which has zeta as a basic parameter, and you constrain what zeta should be for the observations, given the observations of the column density. And these are the compilation of some observations shown in the paper by Marco Padovani again, for the ionization rate ranging from around 10 to the minus 17 or even less, and up to 10 to the minus 15 for different clouds and different methods also. So here the column density of the cloud is on the x-axis. And the various curves show the models I showed before, or what should be the behavior of zeta versus the column density for the different spectral shapes. We had here the low, the blue, or the high, the green, or even the highest, the red. And here they are shown as well. So these are the predictions. And what we see there is a lot of scatter. Some of this scatter could be real from fluctuations, real physical fluctuations in the cosmic ionization rate, because maybe some regions are closer to the sources, some regions are farther away, the fusion of the cosmic rays, physical effects of propagation. And some of it is also systematic, because there are a lot of uncertainty in these models, in this method. You have the chemical models, which need to make some assumptions, like what is the volume density of the gas, what is the electron fraction, and different elemental abundances, rate coefficients for the chemical reactions. All this has to be known if you want to make the predictions. And also you have the observational also challenges. So all in all, there is this uncertainty of how do you go from the observations to measuring zeta. So this is the state of the art so far. Now, a few years ago, I had an idea that maybe we can take a different approach and to measuring the cosmic ray ionization rate. And the idea is, instead of relying on these molecules like H3 plus or H plus argonium, which we all like and love, and they're very nice, but they're trace molecules, right? It's not the main constituent of the gas. And you really are very sensitive to the chemical model for this reason. Instead of that, we can use actually H2, the molecule where most of the gas is, and then you're not sensitive to, you don't need to model it. You know that dense clouds are 99.9% molecular hydrogen. You can use H2 directly to measure the cosmic ray ionization rate. And how do you do that? Well, the same cosmic rays that ionize H2, so this zeta parameter that we want to measure, there is something else that they do. They not only ionize H2, they also excite H2. So the cosmic rays, and more accurately, it's the secondary electrons produced by the cosmic ray ionizations. What they do, they collide with the H2 molecule, and they make it vibrate and rotate, also excite the electrons in some cases. So you excite the levels of the H2 molecule, and then as they fall back to the ground state, they emit infrared photons. And the idea is we want to detect these infrared photons. The intensity of the infrared photons from these levels are directly proportional to the cosmic ray excitation rate of H2, which is very tightly connected to the ionization rate, because there are cross sections that we know the ratio of the cross sections. We understand how much goes into excitation, how much goes into ionization. So this is the idea. Here on the right, I showed the energy diagram of H2. So energy as a function of distance between the two nuclei. And you can see the different vibrational levels in blue, denoted by V. So V0 to V14, that's the 14 vibrational levels of the ground electronic state, and also the more fine separated J lines, that's the rotation, and also the electronic state above. So we mostly, the most important excitation as we find, so by modeling this, is the first vibrational state V equals 1, and that's the most efficient for the cosmic rays. So this is the idea, and in fact, these lines from vibrational and rotational have been observed many times in the past. Of course, we're not the first to do that, but in a different settings. Not from cosmic ray excitation, rather by collisional excitation in hot gas or by UV in PDRs and photodissociation regions like Orion, like we just heard before. So, for example, in a planetary nebula and shocked gas, the gas could be warm, and then you can just collisionally excite these levels. Or in PDRs, you can excite them by UV radiation that can also then emit this infrared radiation in the lines. The infrared radiation we're talking about is ranging between about 2 microns and longer wavelengths. So infrared, near infrared mostly. So these lines have been observed and used to constrain the excitation sources in these kind of regions, in PDRs and shocked gas, but never have they been observed in the context of cosmic rays. So cosmic rays excited H2, that's something that never been observed. And again, the idea, the picture we're having is a dark, dense, dark, cold cloud. So here I show, for example, Barnard 68, a very known, famous pre-stellar core in the Fucus constellation. Cosmic rays penetrate inside, they ionize some of the gas and also excite some of the gas. By gas, I mean H2. And then it falls back emitting infrared photons at about 2 micron, which we can detect. The intensity is proportional to the cosmic ray ionization rate. So this is the idea and the experiment that we've been suggesting. Now we have a theory behind that. We have a numerical theory, but also some analytic approximation. So basically here at the left, where I show the formula, the intensity you expect, as I said, is proportional to this zeta, the excitation rate. There are some parameters that has to do with the atomic physics, like the energy of the transition, the cross section here, this is P, and the branching ratio for different lines, which is basically things we understand from atomic physics based on like things like the Einstein A coefficient and things like that. And also you have the column density of the gas, which you can probe from, say, dust emission or dust absorption, extinction. In fact, this is quite weakly sensitive to this column density because you're on the limit of being optically thick, at which point you're already become insensitive to the column density as well. And we have predictions for also for the which lines are strongest, and we find that the strongest lines are these four lines, Q2, O2, O4, and S0, para H2 lines from the first vibrational state, 1 to 0, at these wavelengths. And this is the pattern that we get for cosmic ray excitation, right? The three lines are very strong, and one line is stronger than the other three, and the other lines, the ortho lines, are very weak because the gas is very cold in the core. So it's about 10 to 20 Kelvin. So this is the prediction from the theory. And in fact, you may ask also, how can you distinguish between different processes, for example, cosmic ray excitation, but you also have UV hitting the boundary of the cloud. Now, the answer is that the line ratios are very different. So for cosmic ray excitation, you get this pattern I showed before, but for UV excitation, you get a different pattern. So this is a typical pattern you get for UV excitation for the different lines. And as you see, the ratios between the different lines is much closer to 1 or between 1 and 2 for the different lines, where for cosmic rays, you really only excite these para H2 lines, the specific four lines. And the reason is the temperature is different in the regions where UV operates versus cosmic rays, and also the process itself is different. One is particles, electrons for cosmic rays, and one is photons. So the quantum selection rules are different. So basically, we can separate and distinguish between the two excitation mechanisms. If we have an observation, we can tell if it's cosmic rays, UV, or a combination, and constrain the intensity of each of these processes, namely zeta and G naught. So with this in mind, we went and wanted to do some observations of dense cores. First, we tried from the ground. This was a few years ago. We used MMT telescope in Arizona to measure take spectrum in the near infrared of a set of 4 clouds. Here I show a few of them, 2 of them. 1 night per cloud integration. And unfortunately, even though you see here the spectrum, here we expected where the yellow strip is to see the line. And you see a strong line to the right, redshifted of this yellow region. This is the S0 line. But this strong emission is not the line from the space. It's just the atmosphere from the ground. And this is after we subtracted the atmosphere from an off position. So basically, this is to say the atmosphere is too noisy to do it from the ground. So we tried and it didn't work. We placed upper limits. We placed upper limits of the order of 10 to the minus 16 for this set of 5 clouds. But fortunately enough, there is a telescope in space that operates in this wavelengths, and that's the James Webb Space Telescope. And so we suggested to make observations with the James Webb. We decided to go for Barnard 68, the cloud I showed you before, and the Fucus. And we predicted, this is the prediction, that we can observe and tell apart the cosmic rays from UV and also constrain zeta very with a high signal to noise
Excuse
ratio.
me.
Yes.
This is your chair, so your time is running out. So could you please just
Okay, I'm
speed up?
finishing. Thank you. Yes. Right. So I'll just skip this. Yes. So we make an observation with the James Webb Space Telescope for Barnard 68, an 8-hour program, and we recently obtained the results. And we were happy to report the first detection of cosmic ray excited H2 in Barnard 68. This is the spectrum we got. So we detected the strong lines in Q2, O2, and O4, characteristic of cosmic rays, as well as the ortho lines from UV excitation at the envelope. And by fitting the model to the observations, we were able to constrain the cosmic ray ionization rates to be around almost 2 times 10 to the minus 16. And here you see the contribution from cosmic rays in blue and the contribution from UV in orange. This is a model of only 2 parameters, zeta and G naught. Basically, zeta scales the blue bars up and down. That's all it does. The ratio remains the same. And G naught scales the orange bars up and down. Again, the ratio is being the same. And you see that the elevated fluxes at these 3 lines cannot be explained by a pure UV model. You really need cosmic rays to explain the observations. So to summarize, we have detected the first time cosmic ray excited H2 in the prototypical cloud Barnard 68. We have future observations in Taurus, or almost 50 hours, and hopefully we'll map more and more clouds in the galaxy to constrain zeta and understand how cosmic ray shape interstellar clouds through chemistry, heating, and magnetic fields. Thank you very much.
Thank you. One very quick question from the audience or someone online. You have online?
There is a question by Helmut Wiesmeyer. No, it's not a question, it's a comment. There may be another way to probe secondary electrons, namely in protstellar cloud void of shocks and outflow, where those electrons could emit synchrotron radiation thanks to the magnetic field. Without cosmic ray, this emission component would not be expected, and there are predictions. So another way to make some measurement.
Yeah, yes. Yeah. No, this is a very good synergy. I agree. I'll be happy if you write me an email and we can talk about this into more details.